Hi everyone. So we will be starting with our chapter 2 um, of high level design series, which is data models and query languages. So uh, let's start. And I will be covering this table of contents as a summary in the end of the chapter. Uh, so let's start. So in the first part, what I want to talk about is something like layering in software and what is data model layer that we are talking about in the topic name, right? Data models and query languages. So um, so we can see our softwares are based on abstraction, right? So there are many abstractions that go into making a software, and there are many layers of abstraction, right? So what we can see in our day-to-day software is different layers of abstraction. Say the first layer may be the application code in API using which is written using data structures in a language, right? So you would use a list, a tree, right? You would uh, you would use other data structures. So all those data structures you use, that you write an application code. That application code is written into a persistence layer, right, which is called a database. So in that also your this the list you are storing at last goes to store into the persistent layer, which is the database. And that data structure persisted in db is usually in the forms of tables, maybe in the form of json documents or xml documents. So this is what is the data model, right? This is usually what is called the data model. Now, below this, what we might store in this persistent layer in disk is those bytes, right? Now, these might be logically represented as tables or JSONs or XML documents, but underlying these data structures are being stored into bytes in some form in the hard disk, right? Now the fourth is bytes are being stored as electronic signals in some form in those hard drives, right? In magnetic drives, they are usually magnetic electromagnetic things, and in SDDs they are solid storage devices, right? So they have some form of how to store those bytes into those electronic signals, right? So in this chapter, we are gonna learn about data models, which is the second point in this, and what type of use case are best supported by each model, right? So what we are primarily gonna talk about is uh, these models, right? Tables, JSON, XML documents. So which of them supports which use case, and what kind of data model is preferable for our requirements, right? So. Uh, Going to the second point, what we are going to do is uh, covering the relational model versus the document model. Now we understand what is a data model. We will be covering the relational model versus the document model. Okay, so first let me define what is the relational model. So the best known model data model is perhaps the relational model, which we all know, which we all study in college, which have stayed the same since the 80s, and to though initially designed for business use cases like transaction processing, which is some sales or banking transactions, airline reservations, and some other things like that, and batch processing, it was able to serve most of modern use case well. So what data relational model is? It is the table structure we all know, right? In which we write the SQL, and for which we write the SQL statements, right? And we store the data as IDs somewhere, like ID might be there here, right? And there might be something like name, right? So uh, and there may be a another for. So we are storing the person data where there may be a phone number, right? So and we represent those data as tables, right? That is the relational model we all know, and that has been the best known model from the 80s, right? Now what, why then the document model came, right? Let's read why then the model came. So why no SQL then? So there are several driving forces behind the adoption of NoSQL. So usually the relational model is called the SQL model, and other uh, models which came as later are usually called NoSQL, though they should have represented something like document model, but document and other models, but they are usually called NoSQL uh, because SQL was the one which was famous. So this was an abbreviated term that was used at the time to introduce new DBs. So and it sticks, so we call them NoSQL, right? So why NoSQL then? There are several driving forces behind the adoption of NoSQL databases, including a need for greater scalability than relational databases can easily achieve, including very large dataset or very high throughputs. A widespread preference for free and open source software over commercial database products. So usually SQL products were commercial database products, and we needed free and open source software. So that's why NoSQL. Then there was specialized query operations uh, that are not well supported by relational model. That new databases that are called NoSQL came to support. And the fourth point was the frustration with the restrictiveness of relational schemas and the desire for more dynamic and expressive data models. So on all of these points, let's deep dive. But on fourth point, I want to mention that, so when we mention the tables, right, it is very restrictive. But these no SQL models um have a dynamic structure which could be changed, right? When you have a table, you might want to add a new column, and then all the rows that were existing in the table would have to be filled in, right? But these structures were very these NoSQL structures were very dynamic, so that's when NoSQL came later. Okay, so we have just gone over the overview of relational and NoSQL models. Now, what I'm going to cover is just a basic part of what is the issue with the relational and what is the issue with the n- document model or NoSQL model, right? And then we are gonna compare them both. So one issue with the SQL model, one main issue was that SQL stores the data in form of multiple tables, right? Like in case of in case of one to many, many to one, and many to many relationships, the data is stored in multiple tables. This is somewhat far from the object that is created at one place in schema, right? So when we create an object in a application, it is at one place, right? It is represented using lists, and so one to many might be represented as list. Then there are relationships that many to one and many to many could have in an application code. But there needs to be a layer that needs to change that objects into the tables, right? So we usually need an ORM layer in between to change our objects into the tables. In NoSQL, directly JSON is stored, so it is closer to object. But to change the objects from table, there was a layer needed, which was an ORM layer, right? So there is sometimes a mismatch between what is represented as an object and what is stored as an table. Uh, so this picture shows, like, if we want to represent a LinkedIn profile as in a SQL store, in a relational DB in a SQL store, what we're gonna do is we are gonna say have a user ID, first name Bill Gates, summary, region ID, industry ID, and photo ID. So our region might be something that is uh, many to one relationship, right? So there could be many users in one region, right? So that is usually represented using a reference. Similarly, our industry could be a many to one relationship, which is also represented using a uh, reference of this, right? In the users table, which has many and one side. So this would be many and this would be one, right? So we keep in many to one relationship, we keep the IDs, reference IDs in many table, right? So we have from industry ID here, we have region ID here. Now, similarly, up our positions. So our positions, we could have multiple positions for a single user, right? So Bill Gates was co-chair for Bill and Melinda Gates Foundation, and he was also the chairman of Microsoft, right? So we need to uh, keep them both, right? So it is a one-to-many relationship. A user can have many positions. So now since this is many and the other part is one, O, we keep it in positions table, and in positions table we keep a reference of user ID. Similarly, in educations table we keep it is a many to one relationship. It is actually a one to many relationship. So we keep the user ID on the many side, which is the education table. Similarly, we can see for the contact info table. So for a single profile, we r- we have to distribute our one to many relationships and many to one relationships and many to many relationships in different tables to accommodate a single profile. And going by a LinkedIn profile stored in a uh, NoSQL DB, which is a document table, what we see is a single profile like Bill Gates and its summary, which is uh, one to one, can be represented here, but one to many also could be represented here, which can be seen here, right? Positions, education, contact info. But but one thing to note is the region info, and we have also left the industries info, right? I will tell later in just in upcoming 5 to 10 minutes why this is so. So we can see as one to many relationships can be easily represented in a document table, which is a NoSQL DB, what we are calling it. So we can easily represent a one to many relationship in a document DB, but many to one was left here, which we will discuss. So we have noted that in SQL, there's an object relational mismatch, and we need an ORM layer. But if we store the but in a NoSQL, what we could do is we can store the object directly. If it contains what relations, one to one and one to many relations, then we can store it directly. Now, coming to the backdrop of document DBs, what is the backdrop of them is they can't represent many to one and many to many relationships. Okay, so in NoSQL, if we store many to one field, like say school of person, we might duplicate this in every document, considering this as text, and have a application level code to handle enum of schools enlisted. But without application level code, there is big issue since this can differ, creating a lot of issues. And also with duplication, if the school name changes, we have to update everywhere. But if we store it by a reference number and change the info now related to school at the up, single reference now, updation everywhere would never be needed since reference number won't be changed since it is not human useful info. So that is the basic concept of normalization done in SQL. NoSQL does not have great support for joins and often need application level implementation of joins. So what this is saying is Uh, so in uh, in NoSQL, if you gonna represent the many to one relationships like a school, say I was also gonna have the school, right? That is represented here, right? Now, what I need to do is for every user, I will be having one this school name, right? Now this is going to be duplicated everywhere, right? So everywhere there going to be a duplication, and this duplication is going to cause an issue because there could be then wrongly named, right? There could be typing issues. Someone might hit his name as in lowercase, so someone might write Harvard in lowercase, someone might write Harvard in uppercase. So there could be issues, right? And this you might have to handle at your application level code, right? Where you would have to define a enum of schools enlisted, right? And but there is another issue is, say the name was changed. Say the Harvard now wants to change its name and remove the public from its name. Say it was first Harvard Public School. Now it wants to drop the public name and it wants to name it Harvard Education School. Then it would have to be updated in every document, right? But in a NoSQL, what was happening was there was a table, right? And in table, this was Harvard was written, right? And it was written at only one place, right? So the school was written at only one place. uh, this could have been made a many to many relationship, in which case this would have been written at only one place, right? which w- the which all of these would have been referencing. Now once this was done, this Harvard would have to be updated at only one place. So, and how we are able to achieve that in SQL while we are not able to do in NoSQL? For SQL, what we are doing is, what we will do is maybe, so I'm gonna show what are we doing in SQL. So maybe this was the schools table, right? With school name as name, I would say, and the ID of that school, right? So say Harvard was 2000 in this number, 2000 with 2000 ID, right? And this was named as Harvard, right? Okay. Now, um, what is gonna happen is, say there was this Bill Gates and other guy, say Jack Ma. Okay. S- So this is the schools table, and this is the, I'm gonna write schools table, and this is the person table, right? Right. And say Jack Ma and Bill Gates both went to school, right? Both went to Harvard. Jack Ma and Bill Gates. Now, since there is a many to many relationship, right? What you would need is an extra table, right? To represent, say the Bill Gates number was something like maybe 10 ID, and Jack Ma's ID was 15, right? Now to represent which person had gone to which school, I would need a third table which might represent uh, admission maybe. Okay, I'm gonna call this table admission. And what is gonna happen is, this would maintain the person's reference 10. 10 went to which school, ID 2000, and that would be all right. And for this it will be 15 and 2000, right? Both of went to the same school. Now what I'm saying is, if in a this kind of format, which is the table format, if we now change the Harvard name, right, we are not gonna change the ID, right? Because this ID is never mattered to the human side, right? What matters to human side is this information. So whatever is gonna change is always gonna change here. So this is gonna change only one time, while this 2000 is gonna remain same for 10 as well for 15, right? So we are what we are gonna change is gonna change for at only one place. But in case of our document table, what we are gonna do is since every document contains his Harvard name, what will have to do is change this Harvard name in every document. For Bill Gates document too, for Jack Ma document too. So that is the problem. So okay. So that is the basic concept of normalization done in SQL. NoSQL could do these things with the referencing these documents, but what happens is it does not have great support for joins. SQL by default supports such joins and is very efficient in those, but NoSQL does not have support for joins and often need application level implementation of joins. So we would need to do code on our side to do such joins. So that's why NoSQL is not preferred for many to one and many to many relationships. The above problem was also faced by IMS, which was the first kind of DB, which was a hierarchical structure similar to JSON as this is shown, which would have a user, some positions, and many to one relationship, one to many relationships represented in this, right? So first name, last name, summary. Then positions would be table, which will have jobs, all three jobs and education. So list would be represented as one to many, and first name, last name, and summary is one to one, right? So similar hierarchical was used by MS, uh, but it also faced the same problem, which was that it was not able to represent many to many and many to one relationships. But this was tried to solve by network model. The problem with network model was that network model was based on pointers in DB, where one node can have multiple parents. This meant many to many relationships possible to represent, but the issue was that accessing paths were left to user. So, what is a network model? I have represented here. So you could see that a student is enrolled in a course in the example, and so how we so there's a many to many relationship. One student can enroll in many courses, and each course can have many students, right? Now student 1 is enrolled in course A, course B. Now this is a pointer, right? Student 1 goes to enrollment, then enrollment, there is a list of enrollments, and for each list there is a course, right? This enrollment represents the student and course both, okay? uh, and this is usually done in a sorted way. It is a sorted data, and this is represented by set structure, which is a sorted data. And the only way of assessing a record was to follow a path from root record, which was say the student, along this change of lines. This was called an SS path. So you would have to just traverse this list, and in the simplest case an SS path could be the traversal of a linked list as shown. Start at the head of the list and look at one record at a time until you find the one you want. So maybe I wanted to find the course 2, right? So what I would do is go from student 1 and follow this path, right, and see if this course is reached. If this course is reached, okay, course 2 is reached, going through this list. Okay, course is reached, course B is reached here, so I will stop here. But in a world of many-to-many relationships, several different paths can lead to same record. And a programmer working with the network model had to keep track of these different SS path in their head. So, say there was also a student too that was enrolled in course B. So, what I could have done is to go to course B. What I could have done is maybe go through student one enrollments or maybe go through student two enrollments, right? And I could have assessed course B from both paths, but I would have to think logic in my head which part I could take. So I could have optimized on that part because I was a programmer and I knew my DB well. I could have optimized it, but this was left to me to save how to traverse this, right? How to traverse this to get data. This was left to me. Though this gave optimal solution, but the whole code for SS needed to be changed if there was some change in structure of model, right? So say I wanted to find the course which had the course ID 202. Okay. Now what I could have done is go over the uh, courses and um, okay. Say I wanted to find the say this had a property, right? Say course had a property something like course has a property something like timing, maybe, right? Timing, and timing is greater than 5, right? Okay. Timing equals to maybe 4 a.m. or something like that. 4 p.m., sorry, to 5 p.m. And now I wanted to run a query where I wanted to find all the courses where timing, uh, all the courses for student 101 which had time greater than 5 p.m. Okay. This was maybe 5 p.m. to 6 p.m., right? Now this was left to me that I would have to decide how I'm gonna traverse this. I would have to write a loop that go over this enrollments, check each course timings, and get me the result, right? Though this might have given me a very optimal solution because I might have come over an optimal solution, but this was left to me. Now, if this structure changed, if I introduced any other column in between, I would have to then again say, okay, go over two columns now to assess the course. So this was very much left to me. But um, in a relational database, what happens is the query optimizer automatically decides which part of the query to execute in which order and which indexes to use. So those choices are effectively the access path. So what SQL provided us was that it by default knows which indexes to use, right? If there was an index or if there was a tree made on this, right? If there was a structure which would have helped me to get this path more easily, those are already decided by the SQL that I could access this path by this pointer, and I could get this by this pointer, and I could execute it like maybe go to the first student and then check all the enrollments and get the timings. So SQL decides all the path. But in this, what I would have to do is I would have to write, okay, go over this, write a for loop for that, go over each enrollment and check. So this was very imperative language, which we call it, and this was a declarative language. So, so network model failed in that sense. Network model was trying to solve this NoSQL problem of many to one joins, but it failed because it had an imperative language. However, today NoSQL are similar in sense to hierarchical model, not in sense they represent one to many model at same level in same document. For many to one and many to many relationship, they differ from the network model in sense that in both cases the related item in both cases, that is SQL and NoSQL, the related item is referenced by a unique identifier which is called a foreign key in the relation model and a document reference in the document model. That identifier is resolved at read time by using a join or follow-up queries. To date, document model have not followed the path of Codacil, which is the network model, network model language, right? So what this means is, so today NoSQL databases have not gone the path of network models to solve the problem of many to one joins. They have rather taken the approach of SQL models only, but in the sense that they also have a reference now, but joins are not very greatly supported still now. So what we do prefer is SQL models since they prefer good joins. Otherwise, NoSQL models also go the same way to support the many to one and many to many relationships. So now we have a brief knowledge about relational and NoSQL models. Now let's discuss relational and document DB as a comparison. So we will compare on these parameters. So which leads to simpler code, right? Uh, so I have written some points here. The main arguments in favor of document model are schema flexibility, better performance due to locality, and that for some applications it is closer to data structures used by application. The relational model counters by providing support, better support for joins, and many-to-one and many-to-many relationships. So which leads to simpler code. So in case of many-to-many and many-to-one joins, if you have in relationships, you should use relation databases. In case you just have one-to-many relationships or one-to-one relationships, you can use a document DB. So that depends on use case. Flexibility. Uh, so in case of schema flexibility, as already told, there is a write time checking similar to compile time checking. So so these are like, you can't put any schemas in these tables, right? If this is noted to be a string, you want to you need to put this in a string, right? And there could only be these fields, right? You can't put another field now in this table, right? If this table have five fields, you can only put five rows or five fields in a row. You can't put a six field uncommonly, right? So they have write time checking, in which they check that this should be a string, this should be a number between this range only. So that type of checking is supported by a SQL. But NoSQL in NoSQL there is a read time checking, right? Read time checking of schema. So you can easily uh, you can easily change in code to assume null if new field is not present in for previous record, right? So in a document DB, what you could do is, this could differ, right? So say Bill Gates had this one, right? But maybe Jackma had user ID and everything, but Jackma missed some points on photo URL. So Jackma might not have this photo URL key at all. But in a in a in a and maybe photo, he might not have photo URL at all, or there might be also an extra key for Jackma, which might be something like scholarships or something like that, right? Or awards, right? So something like awards could be there for a LinkedIn, right? So there could be a fifth unknown field in another document. But in a table like structure, this fifth field either needs to be there for all the values, or there wouldn't be there for any value. But here, for a particular document, there could be an extra key, right? So they differ very much. So in a SQL, there is a write time checking that you need to put this awards as null for all the values. So Bill Gates should also have this value as null, right? And this should have also as this, if this has awards, it should put. But for NoSQL, it doesn't matter if Bill Gates doesn't have this key at all. So that's why it is called in SQL, it is write time checking, which is compile time, that when you write into a database, it checks. But in a NoSQL, when you read it, uh, though there is no checking done by the SQL DB, NoSQL DB, uh, we usually in application code have a schema, right? Because without schema the data won't make sense, right? So we have schema that this data is kept of this type. So that's why we would, once we read from the DB, we would check it on our application code. This is more useful for structures of entities depending on upon external system, or some heterogeneous objects, right? Heterogeneous objects like maybe some e-commerce objects in which you might have to store a medicine as well as a phone in a same DB, right? So those are heterogeneous objects you want to store in a single database. So in that sense, this is more useful. Data locality for queries. So data locality is well supported in SQL also, with the new DBs like Google Spanner, Oracle, and Bigtable. They usually store different tables data close to each other, allowing for faster reads. But still, NoSQL wins here, since they have full of the data at one place only in the single document. But one thing that we need to be careful about NoSQL is we read whole document and update whole document. We can't just partially update it. So we need to keep the documents small and concise, right, and distribute the documents when they differ on functionality. Coming to convergence, these relational and non-relational databases are also converging, right? Relational databases started supporting JSON and XML as fields and giving support to update and query on these fields similar to document DBs. Some document DBs like Rethink DBs also have started supported joins, and MongoDB drivers support joins on client side also. So good thing to see that they are bringing the best of both worlds into single thing. So one of my key takeaways I will describe at the end what we have learned. Uh, so that is all for relational and document DB versus document DB. We can always have one choice that if we have too many to many and many to one joins, we would always go to relational database. And when we want something like flexible schemas, uh, and higher write throughputs, we would prefer document DBs. Okay, so that is a main point I want to take away from this section. Going on to the next section, what I'm going to cover is query languages for data. So we have seen the data models, two of the data models, relational versus document. Uh, Now what I want to cover is what is the query languages for usually querying this data, right, from databases. What type of languages have been developed? So there have been like two type of languages, query languages. One is imperative and one is declarative. So let's go over them. Definition is imperative languages tell the computer to perform certain operations in a certain order. You can imagine stepping through the code line by line, evaluating conditions, updating variables, and deciding whether to go around the loop one more time. So this is kind of like the syntax we write in Java. We kind of tell the computer, okay, go over this for loop 10 times and do this addition, do this thing over this variable. So we kind of define everything, right? So we tell it everything. So Codacel, which we use for network model, was very similar, right? And IMS also worked on this imperative model. That's why there was not much adoption of network model. But in declarative query languages like SQL or relational algebra, you can specify the pattern of data you want, what conditions the result must meet, and how you want to how you want the data to be transformed, sorted, grouped, or aggregated, but not how to achieve that goal. So in a declarative language, what you mean is you would directly ask the result, right? You won't specify how to achieve that result. You won't say that go over 10 over uh, go over this loop 10 times. You would just say, I want this result as a, just get me the multiplication 10 times, right? So I would say get multiplication 10 times, do this 10 times, right? I won't say just write it and write every for loop and every variable. I would just say something like, get me this result. I don't know how you do it, just get me this result. So an example would be, say, get sharks. So in which what you're doing is, if the animal family is shark, you are pushing it into a array, right? And returning sharks. So what you are returning is array of sharks, right? But in a declarative language, what you say is, from animals do what, where family equals to star, get me all the animals what are sharks, right? You just directly get a list. You don't have to iterate over all the animals and check if those are sharks and then push into the result. You just say get me the all the animals where any family equals to stars, and there it directly gives you. So which is better? In imperative code, the list of animals appear in the particular order, right? If the database wants to reclaim unused disk space behind the scenes, it might need to move records around, changing the order in which the animals appear. The database cannot do that safely without breaking queries, right? So if say database animal was here previously, right, and there was some fragmentation in between, right? Here was some fragmentation in between. This was empty space, this was empty space, and now data wants to reclaim source empty space, and this was the animals array, right? Now database wants to move this animals array to some place here, right, to remove the empty space. Here was another query, right? Here was another data. Now to remove the empty space, database wants to move this animals here, right? But in an imperative code, your array would have this address, right? And now if database wants to remove the fragmentation, it would move the animals array here, but you are still running this code with this animals array, right? So database can't do that, since you are reading it from here and you are accessing animals here, right? So if it does that in your query process between, this will fail your query, right? But in an SQL, there is no guarantee where are, since you have not actually written from where we have to get the animals. SQL doesn't carry any particular order. First of all, it doesn't carry any particular order in which you are gonna receive the sharks, right? So it can optimize on that, and also it can optimize on this fragmentation too, right? Eh, since it is doing all the work, it knows what it needs to do, right? It will first maybe remove the fragmentation and then give you the result. So the fact that SQL is more limited in functionality gives the database much more room for automatic optimizations. So declarative language has a better chance of getting faster in parallel execution, because they specify only the pattern of the results, not the algorithm that is used to determine the result. The database is free to use the parallel implementation of the query language if appropriate. This is an analogy which I wanna go to in sense of imperative versus declarative, which is JavaScript. If you say, if you in a web browser want to add a CSS to a particular element using JS, right? What you're gonna do is write the JS imperatively, get that element, add the CSS to that, and then run that JavaScript, right? And this JavaScript is loaded only one time, right? Yeah, at the starting of the page. So this might happen now. This might happen only one time, right? At the starting of the page. But now maybe I wanted to at the at a later stage what, but what's if I just write rather than JavaScript, if I just write it using the CSS files, right? In CSS files you could declare that this element should contain this CSS, right? So that is very declarative in sense of in comparative to JavaScript. And uh, running this CSS, which is a declarative type, again and again by the again and again by the browser, will not yield any wrong result, right? Because what it is doing is just telling what the result should be, and browser would be just getting that result again and again. But this is doing is telling how to achieve that result, right? Now what if I run this 5 times how to achieve the result? This might yield into something other. So if this was a summation function, and if I said this sum needs to be equal to 10, okay, this variable needs to be equal to 10 in the web page, right? And what I was doing for this is in JavaScript is adding this was initially 5, and what in the page starting what I was doing is adding 5 to it, right? So what if I just rerun this JavaScript, what will happen is 5, then again rerun, this would be 15, right? Then this would be 20, right? But in a CSS, what would happen is if even the web browser wants to reload CSS again and again, this would always remain 10, because this only declares what sum needs to be 10, right? It doesn't declare how to achieve that. So that is the analogy between imperative and declarative, and how declarative are helpful. I just want to come. Uh, okay, we will just go over an example of MapReduce, which is a very famous language, which we will also study in later chapters. That is an example of language that is between declarative and imperative, right? So consider a SQL code like this, where what you want to do is you want to sum all the sharks by the month observation month, right? How many sharks you have observed by each month in the year, right? Now this couldn't be achieved in SQL code like this. The same can be achieved in MongoDB's MapReduce like this, right? uh, so in SQL, what you are doing is declaring it this declarative sense. Now that get this observation month, get this sum as total animals, where what sharks family equals to sharks, group by what observation months. Okay. uh, but in MongoDB's map reduce, how you can achieve the same is you could write for you could write first a query basis which it will only get family equals to sharks, right? So it will query all the documents which has family equals to sharks. Okay. So this is kind of our declarative approach, where you have just written what you need, a family equals to sharks. Okay. Now what you are going to do in imperative is you just write what you are going to do for each of these. For each of the rows I got here, what I'm going to do is map it how, get map it through this function, right? Map will run for each of these rows, and for each of these rows what I will get is a key value pair, right? So what has it has emitted, it has calculated the year, it has calculated the month, and for each year month it has uh, it has emitted a key value pair, which is for each month how many observations I have, right? And then what it does is once this is mapped, what I will do is for each of this pair I will run a reduce. Reduce will give me the final result, right? So what I've written in the each key value pair, what I will do is reduce and get the arrays dot sum of each values. So what it will return is return the observation sum, all the observations of all the months I will return to the reduce. So I could get those as the total monthly total reports, right? So uh, this will return what, for each key what this will return is it will sum all the values. So if there was two keys of single month like February 2022, it will return me, say this was 5, first observation was 5. Similarly for February 22, there was a observation, another observation 10, right? It will sum me all the values for this key, and it will return me February 2022 15, right? Similarly for all the keys it will return this, and what we get is the similar result as SQL code. So this part is kind of the family stars is declarative part, and this part is what we have defined as kind of imperative, right? Kind of imperative. Just we have not defined for how many times this need to run. This will run by default on all the result of this, right? Now coming to the fifth, so we have all covered for the this declarative versus query languages. What I will just go over is the new type of databases, which is GraphQL, graph like databases, graph like data models, right? Which is graph databases. So a graph database consists of two objects, vertices and edges. So vertices usually represent nodes or entities, and edges represented the relationships between these nodes and entities. Many kinds of data can be modeled as a graph. These include social graphs, which is vertices or people, and edges indicate what people know each other, kind of like Facebook, Twitter, LinkedIn. These can be very goodly represented as social graphs. The web graph, which could be web pages, and each web page is connected to different hyperpage, right? So hyperlink page. So this, by each page connecting to other page, this makes a web graph, right? And then there could be road and rail networks, in which vertices are junctions of two roads, and edges could represent the roads and railways between them. So graph database are helpful in designing these kind of very complex many to many relationships. Example of heterogeneous DB is in this. So yeah, graph table can be used to store homogeneous as well as heterogeneous object in the single DB very well. And we will take an example of heterogeneous DB, in which what we are going to show is two people, which is Lucy and Elaine, which are married, are living at where they are living, and from where they were born, right? So where here we show Lucy as a vertex, and she was born in state Ohio, which is in United States, which is in North America, and she lives in London, uh, which is in England, which is in UK, which is in Europe, right? And Lucy is married to Ellen, who also lives in London, but he was born in Buin, and which is in something of France, which is in something of Burgundy, which is so something in France and something in Europe, right? So what we are doing is we are representing heterogeneous objects, right? We are representing the persons here, we are representing the states also here, locations also here, right? Countries also here. So these are very heterogeneous objects, right, within themselves. So we are representing it in a single DB, which is the graph DB, and we are representing the relationship as in edges. So there are several different but related ways of structuring and querying data in graphs. In this section, we will describe the property graph model and triple store graph model, and we will look at three declarative query languages from graphs. So this is kind of the graph model, but represent them usually using property and triple store, right? So in property graph, what we do is we we have a vertex which will contain of a unique identifier, a set of outgoing edges, or set of incoming edges, a collection of properties, right? And for and each edge, what it would be, so each vertex would contain what, a set of outgoing edges, right? This would be the data storing, and set of incoming edges, right? And its vertex ID, right? Vertex ID, VID, and a collection of properties related to this vertex other than the VID, right? Similarly, for a edge, what we would need is where what is its tail vertex and what is its head vertex, right? That represents an edge. What is its ID, right? Edge ID, that uniquely identifies it. What is its label, that what kind of relationship it is representing, and what are its properties. Okay. And similarly, we can create an index on the edges, that uh, an index is a faster way to retrieve the data. So we can uh, create an index on the edges, head and tail, right? So we can know which edge tail is, like, create index on edge tails. So by each vertex I could know which edge had gone there, right? By saying this vertex and saying this is the tail of, uh, by knowing this vertex, I could query on the edge DB and ask what were the edges which had this tail as the vertex, which has its edge tail vertex as this vertex that I have, right? So so this way, right, this way to represent this is in relational DB. So our property graphs are better represented as relational DB, in which what we would have is an edge table and a vertex table. Okay, and vertex table would contain this, right, kind of this, and edge table would contain this, and we would have some indexes which will faster our queries. Some important aspect of graph model is any vertex can have an edge connecting with any other vertex. There is no schema that restricts which kind of things can or cannot be associated. Given any vertex, you can efficiently find both its incoming and outgoing edges, and thus traverse the graph and follow a path through a chain of certain of vertices, both forward and backward. By using different labels for different kind of relationships, you can store several different kind of information in single graph while maintaining a clean data model. So these are some points, and uh, note this is different than network model, right? Since network model had the edges and vertex stored in a table, and those fields could be, since this has the edges and vertex stored in a table, and these fields couldn't be indexed, and this is declarative, right? While network model was not. So this uses SQLite syntax, but Codacel was not very declarative. It was very imperative going through the graph, right? So also Codacel had a schema which specified which record could be nested within which other record. This doesn't have any schema. You could associate any vertex with any other vertex, right? So also in Codacel, as I told in the network model while defining the network model, these were all children of a record were written to an ordered set, right? So the database had to maintain the ordering while graph vertices edges are not ordered. So we can access a right. So this is very different than network model, and we can access a vertex directly without writing code, right, leading to declarative SQL statements. Now coming into coming onto the property graphs, first declarative language is a cipher. So cipher uh, So Cypher is a Neo4j DB specific language, though very similar languages exist for other DBs. So I will show one example in which what you could do is, similarly the way we showed our this DB, I will try to define how to define this into cipher language. So you could define cipher in cipher language that there's a North America location, there's a USA location, there's a Ohio location, right? These are the vertices, right? We are defining. This is the Lucy person, and now you could define the edges, right? That Ohio is in within USA, and USA is within North America, and Lucy is born in Ohio. So what we have represented is this graph, right? This part of the graph we have represented as cipher. Now in cipher, uh, finding a person who's who's who was born in USA and currently lives in Europe. If you want to find a query like that, right, what we would need is very simple query like person who's born in this, who could be within, they could be like who was born in some place, right? This represents the some place, this represent a vertex, right? And this represent the edge, right? So a person who was born in any place, right, within, so there would be a within edge, and there could be multiple within edges, right? So this is defining there could be zero or multiple within edges and at the end what we need is a place, a vertex whose name contains United States. So what you would get is a person who is born in United States. Similarly, what we would get is a person who is living in Europe, right? And then once both those conditions are met, we will return the person name. So very simple query in Cypher we could do for retrieving this. Now Cypher helps in recursively trying to include all edges, right? Now, since the property graph model is in fact a relational DB, we can write the above query in SQL too, but main reference is in SQL, right? We need to tell the number of joins to be done, but in Cypher, we let the graph traverse until conditions are met, which is supported by recursive function in SQL as well. So we can write a similar query in SQL in which what we define as a recursive USA, right? In USA, where we see is what is in USA. We see we say what is in USA. In USA is a vertex where name is equals to United States, union to the vertex, union to the vertex, uh, where head vertex is uh, union to all the vertices, un, uh, whose from who edge is going and it is pointing to United States, right? That is what we are saying in USA. So in USA is representing a vertex which is named, which has its name United States. Then what we are doing is a union to edge tail vertex, right? So select all edge tail vertex from edges. So what we are gonna select is a tail vertex, right? Tail vertex of an edge whose head vertex is what USA, right? USA containing edges, right? So in USA vertexes should be its head vertex. Select all vertex. Select all edges whose head vertex lies in USA and return me its tail vertex and union it to this in USA. So this should also be contained in this. And edges label should be within, right? So all vertices which have within, right? Ohio and any other state, right? Say this or Ohio. Ohio lies within United States. So all these vertex would be covered by this in USA. Similarly, in Europe would cover the similar all the Europe vertices. Now, born in USA would cover all the people who were born in USA. You would see, right? And lives in USA, lives in Europe. Similarly, contains all people who lives in Europe. At the end, what we do is join on those born in USA and born in Europe, lives in Europe, and return the name of those vertices. So we could write a query like that with the recursive syntax of SQL, but this was very big queries, right? And this is how small query as a recursive logic, right? So this recursive logic had to be written here. Recursive logic is also written here, but very smallly. So these are graph had so different queries, new queries. That's why I invented. So Cypher is one of them. Now let us quickly jump to triples. So Cypher is usually used for property graphs. Let us quickly jump to triple store graphs. So triple store graphs are usually represented as three parts, right? Subject, predicate, and object. So if an object is primitive like string, it defines a property in subject. Else, if object is a full vertex, it defines an edge relation between subject and object. So a triple graph is something like, see here as an example, a Lucy is a person, right? A Lucy name is Lucy. Lucy born in Ohio, right? We are gonna use the same example here as this, right? So Lucy is born in Ohio. Lucy's name is this. Lucy. Now we define the Ohio vertex. The Ohio vertex as a location type of vertex. Ohio's name is this. Ohio's type is state, and Ohio is within USA. This represent an edge, right? And how we represent an edge? We represent as this two colon semi this colon before that, right? Now USA again defines some properties and now defines this edge of that it is within North America. Again, North America defines some properties of it. So we see that properties here is defined similarly to the edges, right? While here the properties were defined as a different syntax and edges were defined as a different syntax. A concise way to define this would be in a single line, Lucy is a person with name this and born in Ohio. So a concise way of writing this is similar to this. Now we can see is above difference that there is in above there is doesn't define difference between vertex and vertex and edge. Sparkle uses more same syntax to find relation with vertex and to find some property with vertex. So we can say now a query to find a person born in United States, right? In Cipher, where this was an edge and this was an object, we had different syntax like defining this object and defining this edge. But in Sparkle you could see is this edge, right, is similar that there would be one born in edge, then there would be 0 or 1 within an edge, and then there would be an kind of an edge which has its name United States, right? So Sparkle has very much similar syntax because it dimensions the line between uh, relationships and object properties. It has very common syntax of that. The third query I want to define is a functional query to graph models. So we will also again here take the same example. Here what we can do is it is a generalized model, right, where we define functions. So data model is similar to triple store model, generalized a bit. Instead of writing it as a tuple, we write it as a predicate. So what we would do is write name first, and so what we were doing is North America's name is North America, right? In America vertex name is North America. But here what we are doing is name as a function now, right? Type as a function, right? So we define name of North America is what? North America. So we have generalized it a bit. We write the predicate out, subject and object inside. Now in the query what we can do is it helps us make these amazing queries with functions what where we could define some functions and rules, right? So now if I wanted to find a person who was born in USA and living in Europe, what I would do is write this within recursive, right? As a function, as a rule number one, that within recursive is what? uh, Within recursive as a function says that location and name uh, is that if I give a within recursive function with location and name, it would be name location name. So if I give USA as a location and name as something, or if I give as location and name as USA, it will find me the name. It will find me the vertex which has the name USA, right? And within recursive again says the second rule is within recursive is made via within recursive. So USA is made. So USA within recursive USA would contain what? Within recursive location USA would contain what? First, it would contain name of the name of location USA, location vertex which has any vertex which we want to find the answer, right? USA, right? First rule would give us this, right? Only the USA vertex, right? This one it will give, this one it will give, right? Now, second condition what is giving it is within recursive could also contain within and within recursive, right? So within location via, within recursive via name. So what is it saying is, if I say this as USA, I could have this another type Odio, right? Odio is within USA, right? Right. So within recursive would contain this also, right? So it will also contain this, and now this it will contain, right? Similarly, it will contain, yeah, these two it will contain. Now, what uh, born in does is, now uh, now third, what third condition says is, third condition says migrated means someone who has name person, who has name as this, right? So if I say name as this, it should be, if I'm finding name as this, if I'm saying any person, right? Migrated who, this could be a variable, right? Now if I'm saying born in and living in, right, and I'm saying this is who, and I'm asking who is what, right? It will give me Lucy, right? So with this third rule, what we are saying is, give me the person name, right? Who's, who was born in born location within recursive. Uh, so this person was uh, born in this, born in this United States, and it will find all the persons within Ohio. Similarly, living in Europe and all its subgraph like this, and it will at last give me the Lucy name because it only matches the condition, right? So a rule applies if the system can find a match for all predicates on the right hand side of the operator, right? A rule applies if the system can find a match for all predicates on the right hand side of the operator this. So this rule matches if uh, we can find a match for all the predicates on the right hand side. When the rule applies, it's as though the left hand side of the was added to the database. So when the rule applies, we get the left hand side, and our left hand side is then returned to us. So after applying rule one, what is happening is, what we got is North America, United States, and Ohio, right, within recursive. And after applying rule two, what we got is, uh, yeah. So after applying rule one, what we got it is this, North America, USA, Ohio, and Ohio meets it, right? After applying rule 2, what it gave us was, uh, twice, after applying rule 2 twice, what it gave was Ohio is also in North America, right? Similarly, once we get all these rules, we apply the third rule and we get the table, right? So that is all for data log. Um so this helps us make us very good functions, and help us write queries very smallly. So that is all from my side. I will just go over the summary once, since we are running out of time. So what we have done is, we have learned that there is layering in software, and what we are gonna read in this, what we have read in the chapter is data models, right? The second point is relational model versus document model. So there was a relational model intro in which we told about that there are tables, that relation model is actually about tables that we usually have studied from the college, and it has been a very old model which has supported a lot of use cases outside of transactional use cases that it was initially developed for. It has supported large use cases and widely used today only also. Then there are some this NoSQL model was introduced in around 2010, where it was about getting some flexibility on schemas and designing some open source software which were not proprietary software, right? And one of these is document DBs, which we take later, which we talk later. The third point we understood that was relational models have an object mismatch since it represents in table, and in object we have different structures than tables, so we need a layer in between which we usually do by ORMs. The fourth point which we understood was many to many and many to many relationships are very hard to represent in NoSQL, and they can be represented as a reference similar to the relational model, but joins is not very good supported in NoSQL. So whenever you have a case of many to many and many to one relationships, go for SQL. Now, relational versus document DB today, what we understood was taking relational if you want many to many and many to one joins, and take NoSQL if you want high write throughput or schema flexibility. The fourth point we understood was query languages for data. So declarative is better for optimization later than imperative and easy to write. Then we got onto graph databases, where we understood that edges and vertices representation c- in RDBMS can represent graph, and we use cipher declarative query, which is a recursive join declaration in which you join until certain condition is met, right? Uh, so that query really helped over SQL, and that query is used in or similar queries are used in in edge and vertices representation in RDMS of a graph database. The second representation we understood was triple set representation, and we saw the SparkQL with same syntax for properties and edges over Cipher, right? The third query language which was very powerful was data log functional queries made by simple functions, right? So we got over these. Each of these have a use case, right? Whenever you have many too many relationships, very much, right? Or whenever you see kind of a graph like structure, you should go for a graph database rather than a relational database, because then you would have to graph database is optimized for very much queries on many to many relationships. When you want to hop on many things until certain conditions are met, you want a graph database, right? You can't do it with SQL, as you have seen that. Then you would have to write a very bad logic in SQL that uh, do like recursive SQL you would have to write, which was very hard to write, right? So then in those scenarios you go for graph. That will be all from my side. Thank you. This was a long video, so I will try to keep it shorter in next videos. Thank you.